Hi friends of the world, welcome back to the third video of the Q channel. In this video we are going to test a very simplified version of the airflow motor, which is the invention of my good friend Luis Solórzano. We are going to measure the electrical power efficiency of the airflow motor by applying, first of all, with the power supply, we apply a voltage to the DC motor of the fan. The first module is the fan. We are going to apply right now a certain voltage. We start with 20 volts, right? We apply 20 volts, and immediately you can see that the fan blades are rotating. But okay, and producing an airflow, let's check if we can measure somehow the output airflow. I can feel it in my hand, and you can see here the velocity, approximately 1.3, 1.2, but you can see that the blades are not turning, right? Okay, the blades of the turbine are not turning. This means that the airflow velocity produced by the fan, 1.2, 1.3 meters per second, is not enough to spin the blades of the turbine. So in order to increase the velocity, we have to increase the applied input voltage. For an input voltage of 20 volts, and an input current of 15 milliamps, there is an input power of 0.30 watts, all right? And you can see that the output voltage, which is measured by this tester here, is 0 volts, and the output current through this resistor is also 0 milliamps, right? Whereas the input voltage measured with more precision with this multimeter is 1997 volts instead of 20 volts, and the input current is actually 22.90 milliamps, right? So we have an input power, right, but we don't have an output power because the blades of the turbine are not spinning, and that's due to the fact that the airflow impacting these blades is not fast enough, and that means we have to increase the input voltage in order to increase the velocity of the airflow. We are going to do next. At 20 volts of input voltage, you can see that the output voltage across the load resistance is 0 volts, which means that the airflow velocity produced by the fan is not enough to make the turbine blades to spin. You can see clearly that they are not spinning the turbine blades. So we have to increase the input voltage to a higher voltage in order to increase the velocity of the airflow. For example, let's increase it to 30 volts to see whether there is a voltage appearing at the output voltmeter. You can see still is 0 volts, 0 volts, 0 volts, still 0 volts, and we have 30 volts, and still, oh, now there appears a little current, a tiny current, so that means that there is a tiny voltage at the output, but not enough. Let's increase a little bit more. So up to 34 volts. Okay, now we can see there is a reading on the output voltage 0.120 volts and an output current of 13.31 milliamps. We are going to increase now the input voltage to see whether the output and output currents and the output voltage increase. We are increasing now the input voltage, let's see, up to 40 volts. And you can see immediately that there is an increase in the output voltage and now in the output current, 18 milliamps, right? But of course also the input voltage and the input current will increase. These are the values, and we take note of these values, and then with this value for the output voltage and output current, we'll calculate the efficiency also with the input voltage and the input current, the efficiency of the air motor at these voltages. Well, by using the previous measurements of input and output voltage and currents, we'll be able to calculate the input power to the airflow motor and also the output power from the outflow motor, which is, present in this resistor, the slow resistor. Okay, so we have previously that for an input voltage of 1997, the current was 0.02280 amps, and the input power PI was 0.455316 watts. This figure is obtained by multiplying the input voltage times the input current. For that particular input voltage of 1997 volts, the output voltage across the low resistor was 0, and the output current, of course, also was 0. Therefore, the output power P naught was also 0. And when you compute the efficiency, the power efficiency, by using equation 3, you find that at this voltage, the power efficiency of this very basic air motor is just 0. Okay, it's just 0. But then we increase the input voltage to 33.93 volts, and the input current increased as well to 0.05397 amps. When you multiply those two figures, you obtain an input power PI in watts equal to 1.831221. So the input power increased. And as a result, we obtain an output voltage V naught of 0.121 volts and an output current of 0.01331 amps. When you multiply those last figures, V naught times I naught, you obtain the output power of 0.0016151 watts. And when you use equation 3 to calculate the efficiency of the airflow motor at this particular voltage of 33.93, you obtain an efficiency of 0.088, not even 1% of efficiency. Okay, finally we decided to increase the input voltage to 39.89 volts, and the input current was 0.024, sorry, 0.07475 amps, and the input power PI increased to 298.17775 watts, and the output voltage across the load resistor was 0.173 volts, and the output current was 0.01837 amps. And by multiplying these last two figures, we obtain an output power P naught of 0.00317801 watts. And when you use equation 3 once more to calculate the electric power efficiency of the basic airflow motor, you find that the efficiency increases to 0.107%. So not even 1%. As you can see from the previous results, this basic airflow motor actually, for the input voltages we tried, exhibit very poor efficiency, and despite the fact the input power reaches almost 3 watts at a voltage near to 40 volts. However, the output power doesn't reach not even 1 volt. It only reaches about 3 milliwatts. Okay, and that's why the power efficiency of this very basic airflow motor is so ridiculously low. It's negligible. No wonder this particular airflow motor exhibits so poor efficiency, because we are using these components are not optimized. Usually we are using just ordinary fan as turbine and as fan, and also they use ordinary DC motor and ordinary dynamos, with very poor efficiency, and so that's one of the reasons we have so poor efficiency. On the other hand, the empty chamber in the middle of the turbine and the fan is not optimized at all, because in the original air motor of Luis Solórzano, in this empty channel, he puts a convergent nozzle to increase the airflow velocity. In addition to that, in the duct inside the empty chamber, Solórzano places a number of very thin aluminum sheets in order to split this passage in many passages, in order to somehow linearize the wind flow coming out from the fan, which is very turbulent, and in that way he can minimize the losses due to this turbulence. On top of that, the original airflow motor uses an exhaust system that we are not using here. This exhaust system is similar to this one, and it's been designed in order to reduce the discharge velocity in the atmosphere considerably, and so this will reduce the input power required by the fan considerably. So the efficiency of the original airflow motor is much higher. In the next video, we are going to show how to increase significantly the efficiency of the airflow motor so that we can convert it into a domestic wind farm. We'll do this by attaching to the previous airflow motor an innovation of mine, which I call it the Power Efficiency Booster Circuit, or PEB circuit. Until then, thank you for viewing.